Now that we've been introduced to the idea that alkenes can react with hydrogen halides, let's see how that process actually happens. And we're going to look at the mechanism of that reaction. Now we're going to follow the mechanism, and kind of the basic approach of following a mechanism is using curved arrow notation. But we want to go a step further in really understanding why things are happening at the molecular level. So the first step, and this reaction occurs in two steps if we're following the reaction. The first step is protonation. So the hydrogen halide is an acid, and the alkene is then behaving like a base. Bases donate electrons, acids accept electrons. So we're kind of thinking of this as a Lewis acid-base reaction, where the base is the alkene and HCl is my acid. Now, what happens? Well, that pi bond, the electrons from the pi bond, donate to the proton. And when they do that, I now have to, the hydrogen can only have 2 electrons around it, and therefore I have to break that hydrogen-chlorine bond, and the electrons go to the chlorine. Now, it happens that this is an endothermic reaction, and the reason for this is because of the products that result from it. And the product that results from this reaction it's not our addition product, right? I've only added a proton across a double bond. So how do I represent this? Well, hydrogen is going to go to one of the carbons, but the other carbon is going to become a carbocation. So carbocations are typically unstable, and therefore it requires energy to actually, commit to this first step. Of course, chloride is also produced where the electrons from the HCl bond, I'm drawing as red, the red pair of electrons, are from that original HCl bond. So now I've created a carbocation and a chloride ion. The hydrogen went on one of the carbons, and of course in this particular example it doesn't matter which carbon because the 2 carbons are equivalent. We'll see later on, if the carbons are different, how that kind of pans out. But initially, the hydrogen adds to 1 carbon. That's what I want you to know so far, right? And the other carbon becomes a carbocation. So the next step then is what's called an addition step. I'm going to take my carbocation, I'm simply redrawing the carbocation, and I'm redrawing the chloride ion. And now that chloride is going to add to my carbocation. The carbocation is electron deficient, has a positive charge. The carbon only has 6 electrons around it, so it's seeking electrons. It becomes an electrophile. The chloride has a negative charge. It's electron rich, and so its electrons are seeking a nucleus. And therefore, I can donate a pair of electrons from the chloride to the carbon. And this is a very fast process. It's an exothermic reaction. So notice the way that I'm using my equilibrium arrows, right? I have a bigger arrow going to the right. That's a fast reaction. In the first step, it's an endothermic reaction. I actually have to add heat to it to get to form the carbocation. And the next step, heat is actually given off in that process. And the result is I now have my product, my addition product, where I've created a carbon-hydrogen bond in the first step and then a carbon-chlorine bond in the second step. Now, let's take a look at both steps and really think about what's happening at the molecular level in terms of what orbitals are involved with the particular reaction. And so I'm going to draw my alkene again. I'm going to draw HCl. And when I think about what's happening there, the pi bond is interacting with the HCl bond. Well, what orbitals are interacting at this particular stage? So remember in the last video I talked about the molecular orbital of that HCl sigma bond. And we said that, okay, when when hydrogen and chlorine come together, the 3pz orbital mixes with the 1s, and that creates my new sigma bond. So that sigma bond is from the 1s of the hydrogen mixing with the 3pz orbital of chlorine. But that's my new sigma bond. Now, I also produce a sigma star bond. When my pi electrons donate to the HCl, they need to donate to an empty orbital. They are going to donate to the lowest unoccupied molecular orbital of HCl, and that happens to be the sigma star orbital of HCl. And so what happens is I'm going to then take my pi orbital of my alkene and I'm going to mix it with the sigma star antibonding orbital of HCl. So the highest occupied molecular orbital is the pi molecular orbital of the alkene, and the lowest unoccupied molecular orbital is the sigma star of HCl. And when they mix, I get now two new molecular orbitals. One is a sigma bond, that is a carbon-hydrogen bond. The other is a sigma star bond that happens to be a carbon-hydrogen bond as well. And so the pi electrons, right, the electrons are coming from the pi bond, the two electrons. And when they mix, they're going to donate to the sigma star of HCl, and I get a new bond, which is a new sigma bond of carbon and hydrogen. That's the first step. Now notice I also produce a carbocation as well. And now I have a little bit different scenario. So yes, I've created that carbon-hydrogen bond, but I've also created a new carbocation that is sp2 hybridized, right? Because carbocations, now that carbon only has 3 electron groups around it, it actually changes its geometry. It goes from well, it doesn't change its geometry. It was sp2 to begin with. It's still sp2 now, but now I have an empty p orbital because the electrons went to only one of the carbons. So if I take a look at that carbocation, I have to recognize that it is still sp2 hybridized and it has a p orbital. And so I can draw the geometry of it, right? This is the carbocation and it has an empty p orbital. Now the crucial step is that it is an empty p orbital, which means what? It's the lowest unoccupied molecular orbital. So it becomes now the new LUMO. And now what's going to happen? Well, chloride is relatively stable, but it has the highest occupied molecular orbital in that, if we think about an sp3 hybridized orbital, or oftentimes chlorine, you can just think of the chloride ion as having an s orbital and 3p orbitals, not necessarily being hybridized. So what happens? In that second step, the chloride anion is going to then interact with the LUMO of the pz orbital. Right? So this is the LUMO of the pz orbital and the HOMO of the chloride. They're going to mix, and I'm going to create now a sigma bond, that is a carbon-chlorine bond, and a sigma star bond. And when I think about where the electrons are coming from, they're only coming from the chloride. The chloride donates to the LUMO of the pz, they mix together, and I create a new sigma bond. And so now I'm hopefully starting to get a little bit better picture of what's taking place in that particular reaction. In the first step, I have pi electrons donating to the sigma star of HCl, And then in the second step, I have the highest occupied molecular orbitals of chloride donating to the LUMO PZ orbital of my carbocation to create a new sigma carbon chlorine bond.